Hello guys, welcome back to the Self-Help Maths Academy. So now we're going to discuss today about the inner product, the distance, the length of the vector, and then we will see the orthogonality and the Gram-Schmidt process. So let's start with the uh, important thing, that is what is the inner product of the given vectors. So let's understand the inner product. So the definition says that if U and V are vectors in Rn. So here you can see U and V both are vectors in Rn in the same dimension. Then the number U transpose into V is called the inner product. It is called the inner product. It's also called as the dot product. So basically, if you say you have U vector, say U1 to Un, and you have a V vector, say V1 to Vn, then the dot product U dot V is nothing but U transpose into V. This is U transpose is U1 to Un and V1 to Vn. If you consider, it is simply U1 V1 plus U2 V2 and so on up to Un Vn. So this is the dot product of the two vectors. So let us take some example. If I take example that U is equal to say 2 minus 5 minus 1 I have, and V is equal to say 3 2 minus 3, then the dot product of U and V will be, that is U transpose into V. U transpose is 2 5 minus 5 minus 1. This is into 3 2 minus 3. So if I multiply, it is simply 2 into 3 plus minus 5 into 2 plus minus 1 into minus 3. It is 6 minus 10 plus 3. So this is minus 1. So we also have the properties with respect to the dot product in terms of, like, say, the theorem. Now we have the properties of the inner product. Say let U, V and W be the vectors in Rn, and let C be any scalar. C be any scalar. Then the first one is, say, U dot V will be equal to V dot U. Means it is commutative. The inner product is commutative and it is distributive over the addition. That is U dot W plus V dot W. Then if you are having the scalar which is multiplied by U and then you take the inner product with this, it is as good as U dot V or U with C dot V. So all three are same. Then the inner product is greater than 0. Okay, it's always positive. And if U dot U is equal to 0, if and only if U is equal to 0. If any one of the vector is 0, then only the inner product of the two vectors is equal to 0. So these are the properties of the inner products. Then on the basis of the inner product, we have the concept, that is the length of the vector. How do we identify the length of the vector? So the length is basically the norm. The length is basically the norm. Length is nothing but it is also called as the norm of any vector, say V, is the non-negative scalar. It is the non-negative scalar which is denoted by norm of V and defined as, say, norm of V is equal to square root of v dot v, which is equal to square root of say v1 square, v2 square, and so on up to say vn square. And if you want, let's say I don't want the square root, then the norm v square will be just v dot v. So this is the basically what you say, the norm is nothing but it has the relationship between the inner product. You can see the inner product of the given vector itself. The square root of the inner product itself will be the length of the given vector. Okay. So if suppose you have the length of the given vector as 1, if any vector's length is equal to 1, then we call it as the unit vector. And if we divide the non-zero vector by its length, that is, if suppose you have a vector v, if you divide by its length, that is norm v, then this vector is nothing but it is actually the unit vector of a length u. It is nothing but we are obtaining the unit vector because of the length, which is nothing but the norm u. Okay, the process of creating u from v is sometimes called as normalization. Normalization. That is, any vector, if you are dividing by its norm, we call it as the normalization. Okay, so now let's understand the length of some vectors. If you have, say, given vector as u is equal to, say, 1, 2, 3 you have, and the length of this you want, it is simply norm of u, which is equal to square root of u dot u. So u dot u is the square bit itself, that is 1 plus 4 plus 9. So it is square root of 13, 14. So this is the length of the vector u. Okay, and now we have got the distance. We have got the distance in Rn. So distance in Rn is defined by for any u and v vectors in Rn. The distance between u and v is denoted by the length of the vector u minus v. So it is defined by the distance u between u and v will be the norm of u minus v. Okay, so you will find the u minus v first and then take the norm of the given vector. So for example, say you want the distance between the vectors u is equal to say 7, 1 and v is equal to say 3, 2. Then I want the distance between them. Let us find out the u minus v first. So u is 7, 1 minus v is 3, 2. This will give you 4 minus 1. Therefore, the norm of u minus v will be square root of say 4 square plus minus 1 square. This is 16 plus 1, that is root 17. So this is the distance between the u and v vectors. If you have the three coordinates u1, v2, u3 and v1, v2, v3, it is simply the norm will be square root of u1 minus v1 whole square plus u2 minus v2 the whole square and u3 minus v3 the whole square. Now let's come to the important part, that is orthogonal vectors. Orthogonal vectors. So the orthogonal vector is nothing but if two vectors, or you can say the two vectors, say u and v in Rn are orthogonal to each other if their inner product is equal to 0. If any two vectors you are given with, if the inner product of those two vectors is equal to 0, then we say that they are orthogonal to each other. And for a note, 0 vector is orthogonal to every vector in Rn. Okay, so it's very important because you take any 0 vector and you can see that is the inner product of 0 vector and negative vector will be equal to 0. This is true for every v. Hence, we say that 0 vector is orthogonal to every vector. So we also, see that there is something called orthogonal component. Orthogonal component, that if a vector z is orthogonal to every vector in a subspace W of Rn, then Z is said to be orthogonal to W. Okay. See, a vector Z is orthogonal to every vector in a subspace W of Rn. So you have the let's say vector space, and then you have a subspace. In the subspace you have many vectors. So you have got a vector Z which is having orthogonal to every vector here in the subspace of W. So for each and every vector, then we call this Z as the orthogonal complement. Okay. So this is true for every vector Z. Let's see whether the given vectors are orthogonal or not by using the example. Before we go for any orthogonal vectors, so I have one more important definition to be defined, that is orthogonal sets. Orthogonal sets. So if suppose we have a set of collection, let's say a set of vectors, say v1 to v2 in Rn, it is said to be orthogonal set. This collection of set is called as orthogonal set if each pair of distinct vectors from the set, each pair of distinct vectors from the set is orthogonal. So what do you mean by that? So you have a collection of vectors. So here you have a collection of vectors, say v1, v2 up to v2. You take any distinct collection. It may be v1 dot v2, it may be v2 dot v3, or it may be v1 dot v4, anything like this. You take any distinct collection. So for any, say in general vi dot vj, if it is equal to 0, then this collection we call that as, and where I should not be equal to z. If that is there, then we call this whole collection of the set is orthogonal set. Okay, so now let's see if we have the collection here with an example. Say suppose I have given with u1, u2, u3. There is a collection where u1 is given as say 3, 1, 1, and u2 is given by -1, 2, 1, and u3 is given by say -1 by 2, -2, -7 by 2. So let us check this collection of u1, u2, u3 is an orthogonal set or not. So for that, what we have to check, let us consider first u1 dot u2, that is u1 transpose into u2, because the different possibility of the vectors as they are discussing is either it should be u1 dot u2, or it should be u1 dot u3, or it should be u2 dot u3. These are the three possible different distinct vectors. So this is nothing but 3, 1, 1 into -1, 2, 1, which is equal to -3 plus 2 plus 1, which is equal to 0. You take u1 dot u3, that is u1 transpose into u3. So here also it is 3, 1, 1, and u3 is -1 by 2, -2, -7 by 2. Here you can take this as -3 by 2, -2, -7 by 2. Oh, sorry, it is +7 by 2 here. So you can take the LCM. It is minus 3 minus 4, that is minus 7 plus 7 by 2, which is again 0. Similarly, you can take U2 dot U3. U2 dot U3 will be U2 transpose into U3. So here it is minus 1, 2, 1 and minus 1 by 2, minus 2, 7 by 2. This is 1 by 2 minus 2 plus 7 by 2. Again, here you can take 2 as a LCM. So minus 1 and minus 1 by 2. So this will be minus, sorry, this is minus 4 here. So LCM is, so this is 1 2 is, this is minus 8 plus 8 by 2, which is equal to again 0. You can observe all the three distinct vectors, that is U1 dot U2, U1 dot U3 and U2 dot U3. This is equal to 0. Hence, the all possible distinct vectors is orthogonal. Hence, the collection of U1, U2, U3 is orthogonal. This is the orthogonal set. Okay, this is how we are going to define the orthogonal sets. And then we have something called orthonormal. Orthonormal. So orthonormal sets are nothing but the set is, if a given collection is say orthogonal. Orthonormal set is if it is an orthogonal set of unit vectors. That means it has to be unit vector plus it has to be orthogonal, then we call it as the orthonormal. So basically, it actually, then we can say that every orthonormal vector is orthogonal. Every orthonormal implies orthogonal. To become orthogonal to orthonormal, we need the plus condition is it has to be the unit vector. Okay, so that's how we have to check now that whether the given vector is orthogonal or not, orthonormal or not, and whether if it is orthonormal, then how do we check the condition? I mean, if it is just orthogonal, then how do we convert it into orthonormal, but using what? So that's the discussion. So before we go further with the orthonormal, we have some properties. Let's say, say any m cross n matrix and m cross n matrix U has orthonormal column. It has orthonormal column if and only if the U, the vector U, the matrix, if you take the transpose of it, and U, if you're getting the identity matrix, then we say that the matrix U has the orthonormal column. And also it has the properties like say the norm of U into X will be equal to, let U be a m cross n matrix with orthonormal columns and xy be in Rn, then these are the properties which we are supposed to have, that is equal to norm X. Because norm U will be the unit vector, so the unit vector length will be equal to 1, so it is just since norm U will be equal to 1. Then you have Ux dot Uy is equal to just x dot y, since again U dot U is what? 1. Then similarly Ux into Uy, if this is 0, this is only 0 when x dot y equal to 0. Since U dot U cannot be 0 because it is always equal to 1, it's a unit vector. These are the three important properties with respect to orthonormalization. So now, say for example, if the given vectors are not orthonormal, and then how do we convert them into orthonormal one? So that is the important note. So like say if they are not orthonormal, then how do we make them into orthonormal by making them into the, by dividing or by using the normalization process. Say we have to determine whether they are orthogonal or not. If they are just orthogonal, we have to normalize them. So the given vector is U is equal to say 1 by 3, 1 by 3 and 1 by 3, and V is equal to say minus 1 by 2, 0, 1 by 2. Okay, so now we have got the two vectors. So first let us check whether they are orthogonal or not. That is u dot v. So u transpose into v. That is 1 by 3, 1 by 3, 1 by 3, which is into minus 1 by 2, 0, 1 by 2. This is equal to minus 1 by 6, 0, plus 1 by 6, which is equal to 0. Hence, u and v are orthogonal. Now, whether they are unit vectors or not, let's check that particular part now. So, for that, what we need to check? We need to check the norm of u, that is the length of it, that is norm of u will be u dot u, which is equal to, you can check it as 1 by 3 into 1 by 3 plus 1 by 3 into 1 by 3 plus 1 by 3 into 1 by 3. So it is 1 by 9, 1 by 9, 1 by 9. So which is 3 by 9, which is not equal to 1. So it is, the length is not equal to 1. So therefore, we are going to check the norm of u will be square root of u dot u. So this you can consider if you want the norm. So which is not equal to 1 in fact. So therefore what we can say is, similarly you can take the norm of v also, which is square root of v dot v. This again, uh, I can take this as 1 by 4 plus 0 plus 1 by 4. The square root of 2 by 4, which is equal to 1 by 2, which is again not equal to 1. So therefore clearly u and v is not orthogonal. So u and v are not orthonormal. So therefore we have to normalize them. So for normalizing, you know that u you have to divide it by its norm. That is the matrix u you have. So therefore what I do is, it is nothing but the norm u I have already. The norm u we have already, that is, so that is norm of u, which is equal to, you can say, uh, this is 1 by root 3 into, so 1 divided by 1 by root 3 into, this will be just 1 by 3, 1 by 3, 1 by 3. This you will get it as, because 1 by root 3 will be root 3 into, so hence it will be just root 3 into 1 by 3, 1 by 3, 1 by 3. If you take this is root 3 by 3, root 3 by 3 and root 3 by 3. So your 3 is nothing but root 3 into root 3. So hence it will be just simply 1 by root 3, 1 by root 3, 1 by root 3. So similarly you can find the norm for v, that is normalizing v vector by dividing it with norm. So it is 1 divided by square root of 1 by 2. So it is simply root 2 into minus 1 by 2, 0, 1 by 2. So here also you will get, because your 2 will be root 2 into root 2. Hence it is minus 1 by root 2, 0, 1 by root 2. So here you can see whatever the, let me name them as u dash and v dash. So this u dash and v dash are the new orthonormal vectors. That is the required orthonormal vectors. You can check the length of them will be always equal to 1. So this way, if the given vectors are not orthogonal, you can make them as orthogonal and then you can calculate it. Okay. So this is all about the orthogonal and orthonormal vectors. So maybe in the coming videos, we'll see the the Gram-Schmidt process of converting the non-orthogonal vectors into the orthogonal one.